Good afternoon. Welcome to week number 9, lecture B. Today is actually a very important day for us because we are going to learn what P, I, and D. Let me see how many people showed up. Okay, very good. So let's start. So PID controller, we are going to learn today why we need to talk about it and how to systematically tune the PID. Okay. In here, we are going to study a very important concept regarding what we call wind-up phenomenon. It's a very important concept. Okay. Down the road, we are going to learn what is practical differentiator. Okay. So put my chat box in here so I can monitor. And then I'm going to hide the floating. Okay. So first, we are going to learn some basic forms. Then talking about wind up. Okay. Yes, there's a quiz. I already put it in there. You don't see it? Give me a second. So let me double check whether we have it. We should have it. Yeah, we have 09b here. We do. Okay. Okay, double check. It should be there. Okay. Yeah, it should be in 09b. Yeah, it's 09b. Yes. Okay, great. So let's continue. Do you see the screen with a PID here? Okay, good. So basically, we're talking about you have a plant, you have a PID, then you do a feedback. So this is reference, this is output, this is a minus, this is arrow, this is U. So basically, U is a function of E. If I only have this term, it's called P controller, right? I integrate this E, then it's called I. Then d dt is D, right? So it's PID, okay? PID. So remember, this PID input is E, output is U, okay? Output is U. So that's a basic form is in this equation, okay? I want to draw your attention, but usually people do this, Kp times E plus Ki times integration of E plus Kd and dE dt. So that's a usual, we call this is a textbook, okay? This is a textbook format. But this one you are going to learn, this is the industrial format, okay? We'll explain to you soon about why this is important. So today we are going to go through this module, and maybe we'll leave a few items for the next lecture. We'll go a little bit slower, not to be fast. So why PID? Why? Okay. So we know that YPID is most common controller. This is like a feedback control. What do you want? I want to achieve this and this and this, okay? Then we want, what do you want? And what do you know? What do you know? For the PID, what do you know about your plant? What do you know about plant? That's a very good question. You should keep in mind. In why PID is popular? Because we assume we do not know anything about the P, except little bit knowledge. It's called minimum knowledge. And what's that? Keep in mind, keep asking. Minimum knowledge about the P. What are those minimum knowledge? Okay. We'll specify that one later. So 90% of all controllers used in the practice, 90% of them, okay? And sometimes this PID becomes something like this. You have something that is working. So it's two steps. Make something that is working. Usually it's via PID. After that, you try to improve it so that then you to make it work better. So this is called more advanced controls. So that's why we say it's an essential element for more sophisticated controllers. Okay, so if you go to industry, if you can do PID, I think it's even more important than having a PhD. Okay, that's a joke. So is there anything not decided? It's called research issues. The answer is yes. There are a huge amount of issues left for us to study. Okay, so I said I use minimum knowledge. What if I have quite a lot of knowledge about the plant and how I can design PID? What's the answer? That depends on what knowledge you have. So you have different types of knowledge. Then you have different types of strategies. So there are a lot of research issues. And in fact, there are dedicated international conference on PID research. Especially in reality, you have reality issues. It's called reality issues. Meaning in reality, you always have something like this, like, oh, you got some saturation, you got dead zone, you got nonlinearities here and there, and how the PID can be modified accordingly. What is doable? What is not even doable? So all those questions are research questions. Okay. So we keep those things in mind. Okay. So from one of the surveys in Canadian mill audit for paper mill, those making a paper, like you buy a lot of fruits and this the package box, those are the paper, okay? Paper making. So typical plant, you have 2,000 loops, and during the survey, 97 of them using PI, and the rest of percent is like 100% at PIDs. Okay, so and many of those PIDs are not well tuned, so there are a lot of rooms for you to improve when you go to industry. So please learn this one, and you will show to your colleagues that you can tune PID. Okay, and this 75 minutes lecture will lay the foundation for you. So you will have confidence to tune a PID. So this is a textbook. This is a textbook PID format I showed you, okay? So KD, KI, and KD, okay? Okay. So, but this is just a plain form. We have to consider many other things like derivative filter, okay? You have to set point. I talk about this, wind up, and how to do digital implementation. And you have some mode switch. Mode, that means you have a manual mode, you have automatic mode. So many of the system originally is under manual control. So then you switch to automatic control, or something wrong, you switch back to the mode manual control. manual control. So I hope you are not going to, while you switch, you are not going to introduce huge bump. You may damage the system. How we can make the system bumpless transfer between those modes. So bumpless transfer, okay? Bumpless transfer. So this is called wind-up. We're going to learn this one in a moment. So then we better have a mechanism to call anti-windup, AW. So AWBT is, if you never heard about AWBT, that means you actually haven't learned PID control yet. So if you do PI, you don't have the D, right? So when you have a I, when you have the I term, I already told you that if you have a C that is a PI, then you have a P here. So together, these two together will have one of S that is due to the integration. So then the whole thing is at least what? At least type 1, right? Could be type 2 if you have another integrator in here, right? So at least type 1. That means if you have a reference that is step, okay? So then you do the feedback in here. So then this arrow steady state will be 0. So for type 1 system, for step input reference. So here's another way to prove it, okay? Suppose you do have an equilibrium point. This is E0 in here, and your input is a constant, okay? So the arrow E has to be 0. How to prove it? Easy. Because this is U, this is E, so this is integration. So you have a E is a constant, E is times T then, okay? Times T then. So the right-hand side is different from 0. Hence the contradiction. It's contradiction. So it has to be 0, okay? Unless E0 is 0. So this is by contradiction. So a controller with an integration action will always give the correct state by the, if the steady state exists, it has to be 0. So ESS 0. This is consistent to what we learned about system types in the previous lectures. So this is the first issue, 0 steady state. The second issue is regarding derivative. So imagine you have a signal. We assume this is a high frequency noise. The omega is big, okay? So this is the original signal, original. So this is a signal together on top of it, some high frequency, what we call a hairy signal on top of it, some noise, which is this one, okay, this one. We add this one, is okay. Visually, you don't see much. However, if you do derivative, okay, then your omega will coming out. Then you have cosine is a phase change, okay, 90 degrees ahead phase. Then you will come to this way, So this is a black one is because of this omega, okay. So in fact, this is like you have S like this. So you have sine omega here. You have also sine omega, but you have omega here, sine omega here. So because this body plot, you do omega here, so the body plot will have, so this is 1, then this is 0 dB. So you have plus 20 dB per decade, okay? So if the omega is high, then the amplification here is also very high. That's why you have this one, okay? So just giving an example, if your frequency is 100, if even the coefficient is only 1%, it's 1% of the amplitude. Yeah, this nominal amplitude is 1, right? Okay, so only you have 1% of error, of a noise added in that. But after differentiation, it's 100%. Okay, it's 100% error. So better we have something that we can, so this is add noise. This is a derivative. Then you need to do some filtering. How you can remove those things? How? The idea is, so you have S in here. This is bad, okay? But doesn't matter. If I do something like this, so I do tau S plus 1. So what do we call this one? This is called low pass filter, okay? And together, this one is like this, okay? It's called practical differentiator. Called practical differentiator. So usually your body plot will go to infinity as your omega goes to infinity. Okay. But I hope we can bring it down. Okay, so it's low pass filter. We'll bring it down. Okay, bring it down. It will not go to infinity. Make sense? So in here, we introduce a t in here and also t in here, but divided by capital N. Capital N. So if S is very small, as S is very small, so this is a ST, okay? If S is large, then it becomes N, okay? It becomes N. So this is called practical differentiator. So you can tune the T and N, okay? T and N. So what is this N? What is this N? The N is depending on here, how high you want. So I decide this. This is my N, in fact, okay? So here we give you an example. You got a noise, the differentiation, then you do a derivative, okay? Derivative. So then you can see this black belt, a black belt. No. How to do this? Yeah, black belt. It's become much narrow, okay? Much narrow. Okay. So in this case, I did it divided by 5, but if you can divide it by 50, that's even better, right? So we talk two things, okay? We talk three things: Y, PID, and we talked about the PID Y integration will make my steady state 0. Talk about practical differentiation. Now we are talking about forms, okay? Forms. I told you that textbook forms, okay? That is usually not in industry use, but different forms, they can convert each other. Say, for example, this is called parallel form. So you have P and you have I and then D, okay? Then you have gain for overall gain. So these are just called time constant, integration time constant, derivative time constant, okay? Okay. So very interesting. Why? So this is the second, okay? While S is DDT, so you have a second in here, okay? Second in here. So it's second times second, cancel out a second. So the dimension of this one is still, say for example, the same dimension as the E. I mean dimension, okay, dimension. And this is the same. You have a DTE, right? They divided by this T. So dimension-wise, so P, this term and this term, they have the same dimension. Make sense? I think this makes very good sense. Then together, you put a whole gain. So that's industry form. They like this form better. Of course, you can write this format, doesn't matter. For series form, you have a PI, this is a PI, and this is a PD, right? This is a P, this is a D, this is a PI times PD. You get the same thing, okay? So those coefficients can be equivalent, okay? So that is another form. So this is more industrial form. So what's new in there? One of them is called this is the plant. Okay, this is my plant to be controlled. Okay, so let's take a look. So you have a reference in here, but you have a B in here. Okay, so this is called set point waiting. Set point waiting. Minus Y. So if B is 1, this is E, right? So this is E. So this is a real E, okay? This is E. And this is also, this is a minus here, okay? So this is also E. Why? Because R is constant, usually. So ddt will be 0. dr dt is 0. So therefore, 0 minus Y, it is minus. Well, this one you recognize. This is a practical form of differentiator, okay, with this practical low-pass filter here. So this term is a little bit strange to all of us, but this is the industry people invented this. So I want to emphasize the following. If my set point is changing, how can I quickly follow that? You can emphasize that, pretend it's a bigger R, so you can drag it up. So I think when you use your air conditioning on your car, you probably had an idea when in the summer you want this one to cool quicker, so you put those set point lower so you come quicker, right? That's kind of set point waiting. Set point waiting coefficient, okay? So usually you put this B greater than 1, okay? So you can see the B, okay? If the B is 0, I didn't do a set point, okay? But if it is bigger and bigger, then my system will follow faster, okay? Faster, okay? But there's another term in here, it's called F. This F is like a reference to add this as called a reference filter, okay? So this is like B, okay? Reference filter. So this is actually called 2-degree freedom. So you have a method here to emphasize your reference. So that is 2-degree freedom. It's a good way to separate disturbance rejection from the response to reference signal. Okay, reference signal. So this is just called set point weighting example. Okay. So the weighting higher, you react faster. Okay, faster. So here is the first most important point. It's new to all of you. Okay, listen carefully. Because in here you have integration. Okay, it's like a KP, KI. Okay, KI. So KD or whatever. If you have integration inside your controller, and if you have a saturator, so this is called a saturator. Okay, actuator, saturator, which is always true. Okay, because in practice, your control authority is always within a certain limit. Okay, beyond that, you cannot do it. Remember, your op-amp will also have this kind of saturation. You cannot be the voltage higher than the supply voltage, right? So practically all systems will have saturations in actuators, okay? So if you saturate, that means no matter how you change, it is broken, okay? It's the whole loop is broken. So if you have something here unstable, that control will grow very big. So I'll show you an example. So integrator itself is unstable. It will go wind up, meaning pile up and up. Okay, so we need some sort of a wind up protection to avoid that with this integral action. So those instabilities is hard to gain control back. So let's see an example. So the first figure is, so I have a reference is 1. So the system will, this is reference, this is my output. So I purposely, this is 0, okay, this is 0, okay. I purposely limit very small of my control authority, 0.1 minus 0.1. So let's see what's going to happen. So you are going to see that this, because of this arrow is very big, arrow is big, or so you saturate from beginning. So here, you are going to have, you pass 0.1 immediately. So this is 0.1. So you are going to saturate it a bit. But the arrow is piling, still going up. Okay, still going up. Okay, until you see you can see this is still going up. But until you cross this one, you start to going, arrow is negative, then change the sign, then this one is going down. Okay, but the still is still in the saturation state. Okay, until you cross the 0 in here, then you will get out. Then suddenly you will saturate again until to here, right? So this is my 0. Okay, so you can see the control signal will get saturated. Okay, get saturated. So then you can see output, it will oscillate. Oscillate for a long time before they settle. This is really bad. This is really bad. So this is called integrator wind up. If you don't have any mechanism to remove that, called anti-wind up. Okay, anti-wind up, AW. If you don't have this one, you are always like this. And sometimes this could be very big. You keep doing this. Okay, so I want to tell you a story. So it's about 30 to 40 days. In one of the summers, one of my PhD students doing a robot control, make it move. But he said that the robot, when he gave the signal to the robot will spin in place for many turns, then they start to move. Okay, when they remove the command, ask the robot to move another direction, they will again stand here and circle it. Just spin as if like, oh, let me think. Okay, so what is the behavior here? It is exactly this type of behavior. Okay, the oscillates. Okay, the oscillates. And I didn't know, my student didn't know about this anti-wind up. Okay, if he somehow put an anti-wind up scheme, then it will something like this suddenly. And so without those stuff, okay, like this. So you can see only 10 seconds, it will settle down. The other one is 60 seconds to settle, right? Okay. In extreme cases, maybe it's very long before you settle. So this U is, you can see, is a saturate, still true, initially the saturate, but it will get out of the saturation as soon we cross here, then they will come to here. So that is called anti-wind up. How they made it? So it's due to this picture, you should remember. I may ask you to draw this anti-wind up scheme. So you have a plant in here. I'm not drawing the plant. So this is basically control signal you add to the, so you have actuator. So before the actuator, so you have saturation here, right? Saturation here. Because of the saturation, so the whole thing from here to here is called anti-windup mechanism. And then, of course, this is a P, this is a D, this is I. Okay. So what they do is to remove. Okay, to remove. So if I didn't put the negative sign, that means plus. Okay. So basically, I try to shovel off, to remove, because it's saturated. Then I bring this saturation. So if it is in here, non-saturated region, then this is 0, okay? Because in and out are the same. But if somehow this is saturated, that means this is V, this is U. So V will be greater than U, right? U is clamped, okay? V is bigger. So then this is a negative. Then it will remove from this signal. So if I get saturated, I'll use that information to pull off, to get out of the saturation as quickly as possible. So this is called anti-windup mechanism. And if you don't have this one, your system will never work. If it is illegal, it is illegal in real systems without using this, okay? Without using this anti-windup, because in reality, this saturation is always there, no matter what. It's physically there, okay? Never ignore it, okay? Sometimes you pretend you can ignore, but we are talking about practical issues. So in practice, never ignore this one, okay? So if I say, can you show me anti-windup PID controller with a practical integrator? Oh, sorry, practical differentiator. You should do that. So remember here, I'm supposed to do a y, r minus y, okay? But remember, r go to the s will be 0 because you have a constant reference. So then it's 0. So then I only need to use minus y to feed into this one to get a d. So r minus y is my k. So this is also k, k, k. Okay, so I have a same, so I have a bracket, parallel form, you have k. So here you have E plus, this is a T, ds plus 1 over TIS. So TI is here, okay, 1 over TI. So it's integration time constant. This is a differentiation time constant. But is this the one we want? No, it's not practical. So the practical one is 1 plus TDS divided by N. What is the N? Usually the N should be like, okay. Usually it's like N is should be 4 to 40-ish, okay? This is empirical. But remember, you also have something here. This is called anti-windup time constant. So if the T is going up, then your amplification is going down. So if it goes to infinity, then it is like 0, okay? It's no anti-windup. So when TT is infinity, very, very big, that means as if you don't have this mechanism, okay? So let's check different TT. So T is bigger. If T is small, T is bigger. So when you have a small means you have a large, so when TI is small, this one's small, that means this guy is bigger. So this you have a very strong anti-windup. So you can see here, this is the strongest, it's here. So the T is 1, is around here. 2 is here. 3 is here. Okay. So if we so TT is infinity, then you are going to get something like this. Okay. Okay. All right. So then your robot will spin in place for 30, 40 days. And this is very funny. Okay, this is a real story. And then when I point to him, he's surprised. He never learned in the classroom setting. So I feel like this part must be in our class for our mechatronics students. Must know this one. So not to waste another 30, 40 days try to figure out what's going on. So anti-windup, very important. Otherwise, you end up on this curve, okay? Okay. And this is how quickly they get out of this. They get out of this, how quickly they get out. So you can see when this is stronger, so they can get out of this quicker, okay? So if otherwise TD is infinity, what they have? Something like this, okay? So as you can see, this is a very simple idea, but it's usually ignored and not taught in a classic textbook. So please remember this. I'll check you in final exam. Most likely I will, okay? So anti-windup. I hope this is something new you will never forget, okay? But there's a rule of thumb, okay, about how to choose this thing. Usually choose half of the integrator time constant, okay? Okay. And sometimes you also, when you have derivative, okay, then what you do is you do square root of this one. What's this? This is actually is called what? Geometric average, right? Geometric average. Geometric average. Okay, so so how to digitally implement this one? Today I probably will not go through with you on this one. We are going to learn digital control. We are going to revisit this part. Okay, so we'll quickly go through. So digital means you have an analog signal. You need to go through a chip. There's a chip. That chip will make this AD converter so that this is a digital signal. Okay. In our textbook, we have dedicated section explaining how this works. Okay. Okay. So then we need to talk about sampling, how fast we sample. And if we don't sample fast enough, we are going to have aliasing. We are going to learn after the spring break, okay? And then how to convert differential equation to difference equation. And then how to do bumpless parameter change and word length issues. All these practical issues where you implement the PID control in digital form, okay? So this is for so this is called interrupt service. So when you have a clock, this is a clock pulse. When you have a clock, okay, so then this clock for interrupt, so then the whole processor will go to something called RSR. It's called interrupt service routine. Then the UPID is implemented in that service routine. Okay? So this is called interrupt based. Okay, but today you guys are not using this interrupt based at all. So we don't worry about. We'll go through this one again later. So we are going to skip this part quickly, but let you see. So this is a P controller. This is the I controller. So the I controller will keep adding. So this is a U minus V, you remember, U minus V, okay, U minus V. It is supposed to be 0, Okay, so this is U minus V is this one. So U minus V. So input is V, output is U. So it's something like this. So this is V, this is U. Okay. So otherwise they keep adding up. This is a keep adding up. It's an integration. So we're going to go through that one later. So this is saturation is V. V is the input. Anyway, so this is called bumpless transfer. So this is called automatic mode. This is called manual mode. So when you have a system you're doing here, so this is called when you turn to manual mode or manual mode to automatic mode. So between three modes: manual mode, automatic control mode, or off. Okay, or off. So we hope we are not going to induce or introduce additional transient due to that. So this is called bumpless transfer. Okay. So bumpless transfer, basically, you have a saturator, you have an actuator. So then in the end, so you have a plant in here. We are not drawing this other parts. So we just to let you see, you have a PID output in here. Okay, so then this is your PID control output. So this is set point, is your reference. Okay, this is basically your measured variable. It's a set point, SP is R. Measured variable is Y. Okay. So, and this is the saturated control signal. Okay, saturated. So this is for anti-windup. Okay. So inside this box, we already showed you it is something like this. So inside the whole box, the PID box, okay, is something like that. Okay. So when we put into this box, okay, put into the box, then outside we need to have some sort of manual mode versus automatic mode, automatic switching. Okay. So you have a manual mode whenever you put on here. So this is a manual mode. So you have the manual input. Okay. It's just like remember when you drive a robot. So it's called joystick mode. Joystick mode. So its joystick is played by you, right? So joystick mode. So when you turn it here, it's joystick mode. But if I turn this one back in here, I hope I can be smooth. So in this way, those manual feedback, okay, so these are the same, okay, this is a copy of it. So all the signals are the same. So it will come to here as well, okay. So they call it external set point, okay. So in this way, the system will not get bumped up, okay. So that is a basic concept of bumpless transfer. Okay. So for any of the commercial PID controller you buy from off the shelf, there are so many different companies. Okay, so many different companies. So they have three different types. One is called Series, one is called Idea, one is called ISA. Okay, International Society of Automation. So different company using different formula of the PID. So whether they have a set point weighting or not, a derivative, practical derivative imitation. See, sometimes they get 8, sometimes they get 10, some of these get 3.3, or sometimes it's even bigger, and so on and so forth. Sampling periods, okay? So you can see these are on the second. So it is usually in the small, slower system. So this is small, okay, like 36 millisecond. Okay. So some of them are big, like 1 second. So those are for slow system, like temperature, like those process controls. But if you like a very fast system, like a motion or robot, those probably need to use some faster sampling rate. So let's revisit the ISA. This is ISA. This is parallel. This is serial. Okay. So the KC is the overall gain. Okay, gain. So the set point of the signal reference is giving this. This is feedback. So this is arrow. So it's very interesting. So if you have a C in here, so usually this is a constant. But if you my constant also doing something like this, some steps reference is constant for a while, then constant again. So when you have this kind of change, I hope I can quickly follow you. So they use this C to tune that. Of course, if C is 0, then it's nothing, right? It's like constant. It's like constant. C is 0, but it depends on how often you change, how big is the change. So this is a practical differentiator. Okay. Okay. So makes sense. Makes sense. So these are called set point weighting factors. One is in here in P controller, one is in D controller. Okay. And this one is so this is a standard. So this is actually a series. Okay, I'm sorry. So this is a series. So this is a parallel. This is a parallel. So this is a textbook. Okay. So this is P. This is I. This is D. Okay. This is D. Okay. But they have their own individual gains. Okay. Individual gains. I think this is interesting. Okay. And remember, if we are talking about the serial form, that means I have yeah. So you have PI, you have a P, you have this one PD. This is like a practical. This is a practical D. Okay, 1 plus like P and D. This is P and I. Okay, this is P and I. This is P and D. Okay. So the reason they have the 2 is because, okay, it's because the set point weighting issue here. The C is the set point weighting issue. Okay. And remember, if S is 1, C is 1, B is 1, then you can merge. Okay, you can merge. Then you have a SP and Y. YSP minus Y is my E. Okay, it's my E. But now they split this one, so this serial form is a little bit special. So in summary, what is A? Anti. What is W? Windup. What is B? It's bumpless. What is T? Transfer of different modes. So I'm going to flash you how we do that. So basically you have this is a this is a PID control with a practical D, but without anti-windup mechanism. So that's my former student spent 30, 40 days to debug and cannot figure out until I take a closer look. I said, oh, did you add anti-windup? He said, what is anti-windup? I know he's stuck in there. So you have to put this anti-windup. Did you see it? Okay, but is this enough? Maybe not, because we don't have an anti-windup in there. Oh, we have anti-windup for PID, but we don't have what? We don't have the bumpless transfer, smooth out. So this is anti-windup, bumpless transfer, okay? Bumpless transfer. So the bumpless transfer is to pull out the signal in here compared to here, okay? So we use a parallel PID as an example, anti-windup. Then we do a manual control. So we hope we can have AM, MA, AM, MA, bumpless switching. So that is the architecture. That is the architecture for that. All right. So we talked about PID so far, but we haven't really addressed how we decided those KP, KI, KD, those parameters. So that's called parameter setting method. So I want to decide. So basically, what do you want? Okay. And what do you have? Okay. After that, you say, oh, now I can design a controller. Design a controller. So this design controller, we also have two parts. Okay. The first part is called, what is your controller's structure? What is your controller? After you decide the structure, what are the parameters in the structure? So basically, we solve this problem. We decide to use PID as a structure, but we haven't decided about what is the parameter, how we do that. So this is kind of like, what do you have? So it's called modeling. Okay? What do you want is modeling, then you do control, then you do analysis to see whether those specifications are met. This process is called analysis. Okay. So then the whole thing about how to come out a controller is called design. Okay. Of course, the design structure, you also design parameter. There are some deep theory regarding how to design structures. We'll probably find time to cover a little bit on that. There are so many other structures in addition to PID, how you can pick up the right one. Okay. But again, to do that, let's talk about what do you want first. What do you want first is basically talking about requirements and objectives, right? So then this is a typical control. We talk about noise, talk about disturbance after the plant or disturbance in front of the plant. So this is the plant, right? So after is N, in front of it is D, okay? In the motion system, motion control system. So this is like at the position level. So this is like a torque or current level, okay? Kind of thing. So the torque disturbance versus measurement and noise in the measurement. So this is a feed-forward filter, okay? You just think about this is one, okay? This one. So if this is not one, and you say this is another tuning knob, so then we call the system is 2DF, 2DOF. So this is a 1 degree of freedom. You design it. This could be another one. Okay, so the first degree of freedom, the second degree of freedom. So we usually use 1 degree of freedom. Let's do that first. Okay. So what do we want? We want the load disturbance can be reduced. We don't have too much measurement noise. Sensitivity is low if you have some fluctuations in here. So your real system is a nominal part and delta P of S, P0 of S. So this is a nominal part. This is just uncertain, unsure part. Okay. And also, I hope if you have change in your set point, I'll quickly follow you instead of waiting long time. So all these are what I want. So design objectives, sometimes people need to make a trade-off between speed and stability. So if you want something really fast, okay, then it could go something like this, okay? So it becomes very oscillatory. So in classical sense, people may say, I need something that is oscillatory. But if you say I don't know, I like oscillator, then you probably will end up with something like this. So very slow, very sluggish. So you really don't want that too slow. It is too slow. I don't need it. So usually you can tolerate some sort of overshoot, okay? And then you have another overshoot here. So this is called A2. This is called A1, okay? A1. So A1 divided by 2, usually this set is 4 is considered as, in practice, is acceptable, okay? So when they do that, if this is 4, then this damping ratio will be like this, okay? So you can do this classical design. But how they come out this magic equation? Excuse me. So I want to remind you that we have a raw model that is second order. So it's 2 cos C omega n S and S squared. So this is, we're talking about this raw model. Okay. So I want to design a system to behave like this, okay? So this is the design objective. So this is called a good trade-off between speed and stability. So this is considered as a common practice. So you need to understand first called qualitative behavior change. So if you increase the KP, then the speed will increase, but your stability will reduce, okay? Well, this is a controller, okay? This is a controller. But if you keep this KP constant, others can only change the TI, you increase it, that means this one decrease, okay? Then your speed will reduce, okay? Then your stability will increase. Same thing here, you have TD. You increase the TD, increase this one. You are increasing the speed. Your speed will increase. And your stability is also increase, okay? This sounds good, okay? This sounds good. So that's why D controller is sometimes very helpful if you use it properly. But this one will give you lots of noise amplifications. And the D, if you do not use well, you actually will mess up things, okay? Mess up things. So I think how to use the D properly becomes an art. That's why in industry, they said 93% of the controllers are PI and the PID is 7%, okay? That's a survey. Because this D has more requirements to tune it, okay? So lots of people simply do PI, okay? So here's something called Ziegler-Nichols step response method. So here we are going to answer. We haven't assumed that we have a controller, we have a plant. So we talked about what do we want. I want a system to behave like this or like this. But we haven't answered about what do we have. Did we assume anything on this one so far? No, we haven't. Okay. So now we are going to have something assumed. What do we assuming here is being able to do a reaction curve. So this is called a reaction curve. So this is usually in practice possible. You have a plant, okay? So before I control you, so let me check. I put a step. Then you'll have something like this. You have something. You have delay. Then gamma here. So then eventually you settled at a certain value. So this is exactly this thing is called a reaction curve. Reaction curve. So then this is input is here is this blue curve. So you have a step and see how it reacts. So how it reacts. So let's do this after a while. This is settled. Then I have a delta y. This is here delta y. Delta u. How big is your step? This is easy. So it's just like a steady state. Your output divided by input. So this is actually called static gain. Also called DC gain. Because I do not know what is my PS, but I do know my PJ0 is KP. This is called DC gain. Omega is 0, right? So this is one parameter, KP, okay? KP. Another parameter is called theta. What is theta? Theta is L divided by T. What is L? L is where you can start to, so this is the, this is, this, so this is the leaving the 0, okay, going up, all right? So reaction, okay? So then I choose a point that has, okay, so that has, because this is after this point, okay, after this point, all the slope will be reducing, okay, will be smaller and smaller. So initially you have slope is larger, then smaller. Then starting from here, you will be always smaller. Okay. So this is called flexion point. Okay, flexion point. Then you draw this line. Then you start to draw this rectangle. So you are going to see this is the important point. So you choose this one as T. Okay, choose this one as T. And the starting point L, or L, could be pretty small probably. Okay, so this L divided by T, this L divided by T, okay, is called theta. So what I should do here is to put a table, okay, put a table. You get LT and DC gain, okay, set point, get LT and DC gain, and L divided by T is theta. So if I choose P controller, what is my KP? What is my KP? The KP should be choosing 1 over KP times theta, okay? 1 over KP times theta. But if I use PI, then I do a 10% discount here. And TI will be 3L. If I do PID, I do this one, okay? It's a larger gain. Then TI is smaller. Then this is half of this. So this is called, what do you know? I know a reaction curve. Okay. Then how you can come out the control design? This is called tuning table. So unfortunately, this tuning table is from Ziegler-Nichols. So these two guys, in 1940, perhaps. Okay, I forgot. Maybe it's 1942. Need to double check. So they did a survey of many plants and summarized a table like this. Okay, I got like this. And since then, when people follow this table, follow this reaction curve, then do this table, then you put on the real system, it will work. Okay, so maybe people may say, oh, this is maybe a quick and a dirty. I didn't know the whole thing about my PS. So it is minimum knowledge. Basically, you have 1 point. Basically, you have 1 point of Nyquist plot. Okay, Nyquist plot. I remember you have a plant. Okay, this is a real part, imaginary part. So then you have a, well, omega is 0 is a constant. So this is DC gain. This part is DC gain. Okay. Then omega goes to infinity, they go to here. Okay. So this is famous Ziegler-Nichols tuning table. So there are two versions. This is the first version based on reaction curve. What do you have? I have reaction curve. So do that. But what if I don't have the reaction curve, but I can do something called critical oscillation method? Okay. So what you do is, this sounds very silly, but people do this. Do this. Where is the table? Yeah, this is the table. So don't look at this one yet, okay? Basically, the idea, so I'm talking about the second idea of Ziegler-Nichols tuning table. The first one is based on reaction curve. The second table is this one, okay? This table is also widely used, okay? So depending on which one you need, okay? So what they do is, give me KCU. Then I can use all this. This is like a little bit smaller, okay? And this is this bigger. Remember that is 1.2, this is 0.9, you remember. But it's okay, so let's do that. So KCU is, so you have a plant, your PID control, you just put a KP here. Okay, no, not KP. You just put a K here. You put a K here. This is your step, okay? So then you have a K, then your system like this, okay? You increase the K, your system will be like this. You increase again, you oscillate more. You increase very big, then your system will be unstable, okay? Will be unstable. But what if you just tune the K such that your system is sustaining oscillating, okay? Sustaining oscillation. In that case, okay, so it's not going up, it's not going down, okay? So that is called, K is a critical gain. So this is called KC, critical gain, okay? KC, okay, KC, okay? Some people all call this as ultimate gain. Because if you have a gains bigger than this guy, bigger than this KCU, the system will blow up. If the KCU smaller, then it will have oscillation and die out. Okay. So only when you have a sustaining oscillation, you write down you write down what is the K. Okay. What is the K? And denote the K as KCU. Then you put the KCU here. Okay. KCU here. And you also measure what is the period. So the period is called PU. It's called ultimate period. Ultimate period. So yes, you can do that, right? Ultimate period. So you measure it. So this PU, put it here. So you have KCU, PU, put it here. Use this table, and you can set this the second form of Ziegler-Nichols tuning rule. Okay. But at this point, you should challenge me. So you can say, hey, Dr. Chen, if this is a nuclear power plant, you make the nuclear power plant sustaining oscillation, maybe it will explode. I don't want to do that. So you want to get it to control, first you destroy it. So what's the point that you control it? So this idea is a bad idea. But if you do simulation, Simulink, will you be able to destroy it? No, you just try and error. You can do it, right? So if you do simulation, it's okay. You don't want to do it in a real system. So that's why simulation is good. So it's still of value. But in practice, I still can, I want to go to this way. There is a method to replace this kind of brute force. I want to say this is brutal in a sense that basically you probably will kill the system, will damage it, will damage the system, right? I don't want this. Although the idea sounds cool if you simulate, but in practical system, if you are facing a system, you do this experiment and may destroy your system, right? So can I have some other ideas? So that is called auto tuning approach. Okay. So let me do this. This is not important. Okay. So we try to, this is called a relay property. So it is positive, then this is 1. It's negative, is -1. Okay. Relay. So I put this relay to the system. Okay. Put the relay to the system. And I'm going to do this. So I have a plant in here. This is my output. So instead of put a KP here, put everything, I put the KP and put the KP very big. I don't do that. I don't want to constrain. So I put something here. I don't put anything. I just put this guy in here. So I see this E is positive. I do 1. Okay. This is okay. You are not going to destroy your system, right? Okay. You are not going to destroy your system by doing that. So after that, you put instead of the KP there, you do a relay. Put a relay in here. You are going to see your system will be either, so here, so you have a system either like this. So this is a control variable, UT. This is output variable. Okay, this is an output variable. So this is a control variable. Okay. So this is U, this is Y. Okay. Because U is only positive or negative 1. Okay. It's relay. Okay. It's relay, like on and off, that kind of thing. Because of that, then the system is behaving like this. And the E is opposite sign of this. Okay. E is R minus Y. Okay. So then this is also, then you go through this relay. So then the system is always like with this oscillation is much smaller. This A could be much smaller than those oscillations, okay? So because you can make the system just like perturb, okay, on and off, make it small, okay, make it small. So you got a PU in here, and you got 2A in here, okay? So this is called peak to peak, okay? Peak to peak is 2A. Remember, you also have peak to peak, you have 2H. So actually it's 2, but H is something you can put again. If you feel like this is too big, you make the H small, okay? Then A will be also small, okay? So A is a function of H, okay? Make sense? So in this case, you don't need to worry about the pushing the system to the boundary of stability and instability. So you're not going to damage anything. So then you can use this H, A, and PU. So PU is the same here, but H and A, you need to go through this 4/pi. So why this is so? This need like a 1 hour mathematics. Okay, it's in the end of this deck of slides. Derive it using something called describing function. We don't have time to do that. So by today, we visited the 2 Ziegler-Nichols tuning method, the table. One is for reaction curve, another one is for relay experiment. So do a relay experiment, you will get these parameters. But this table is the same table as we push this guy to the ultimate oscillation. That ultimate oscillation could be dangerous, so it's not usually used. But in reality, in simulator, you can still use it. So with that, I think you can answer all questions in the quiz. So we're going to continue to go through the PID, some practical issues left over, okay? With that, we can finish today. Any question? When will quiz 9b be published? It is published. Really? Oh, let me double check, okay? Let me double check. Yes, the spring break take-home exam I'll send you soon. Okay, so let me check what happened to the assignment of the quiz. This is strange. That didn't happen to me. Oh, available until March 19th. Oh, maybe it's due to that went available. Wait a minute. It is available. Due tonight. Available 2:30 p.m. So save and publish. Can you guys access the 09b? Can you try? Can anybody try whether you can access it pops up now? Oh, really? Yes, it does. Okay. Then have a good weekend, okay? And wear a mask when you go anywhere during spring break and protect yourself, okay? Oh, have a question? What is the exam due? It should be due after the spring break, of course. Yeah, maybe a week after. Give you enough time. Yeah, we'll give you enough time. Okay. Take care.
Professor, I have one more question.
Yes.
Will you be having office hours at all during the spring break?
If you want, you can make an appointment with me.
Okay, sounds good. Because I have a question regarding another project that I think you might be able to help me with.
Lab or?
Capstone.
Oh, capstone. Am I assigned as your faculty mentor?
No.
Who is your faculty mentor?
We have Abel Chuang.
Yeah, you should ask him first.
Okay, sounds good. I appreciate it. Thank you.
Then you can keep me in the email loop. So
Okay.
maybe I can throw out some of the ideas useful to you.
Okay, it's because we have a we're working with some batteries to make a.
He's the real expert on that.
Okay, yeah. So I'll email him and then I'll follow up with you.
Yeah, definitely.
Okay, thank you.
Take care. Sorry for extra time. Bye then. Should we expect labs to be graded, Professor? Oh, it will be graded. I'll remind them to grade. Okay, this is a lot of work. Okay, bye.